Okay, so 21B workshop. Today is the 22nd of February. So trig integrals. And I kind of think of this first as powers of sine and cosine. And there's three separate situations we can encounter here. The easiest one is when you have one of them to an odd power and one of them to an even power. So if we have an odd and even power. For example, the integral of cosine cubed x sine squared x dx. So whenever you have one of sine or cosine to an odd power and one of sine or cosine to an even power, you're always going to let u equal the one that's to the even power. So we're going to let u equal sine of x. Okay, here's the real truth about these powers of sine and cosine problems. You're trying to make a choice for u so that the non-u thing, in this case cosine, after you deal with du, you want an even number of your not u thing to be left over. Let me show you what I mean. So let u equal sine, du is cosine of x dx. So I break off the part that's du, and I like to do it this way. I'm going to rewrite this as cosine squared x sine squared x times cosine x dx. I know you guys like to write dx as du over cosine. I'm really not a fan. There's my du. And now I'm going to say again what I said before. My non-u thing, cosine, the leftovers are raised to an even power. And when the leftovers are raised to an even power, that means we can use a trig identity. What we're going to do is we say, oh, cosine squared of x is equal to 1 minus sine squared of x, which is 1 minus u squared, because u is equal to sine. So this sine squared is just going to be u squared, and this cosine squared is going to be 1 minus u squared. And that's the idea, really, when you have powers of sines and cosines or secants and tangents, is you're trying to make a choice for u so that the thing that wasn't u can be turned into the thing that is u via a trig identity. That's always the idea. So here we're going to end up getting the integral of 1 minus u squared times u squared times du. We multiply out the integrand. We get u squared minus u to the fourth du. We integrate. We get u cubed over 3 plus u to the fifth over 5 plus a constant. And then we do something. Oh, then we plug back in what u is equal to, which is sine x. So we get sine cubed x over 3 plus sine to the fifth x over 5 plus c. You here for 21b? Welcome. Let me give you the hand that I've given everyone else. So this is kind of an integration flow chart and what questions to ask yourself if you are trying to figure out how to integrate a certain type of thing. Questions about this one?
Why does the sign in front of u to the fourth after you integrate turn to positive?
Because I made a mistake.
Okay.
Yeah. It should be minus. Sorry about that. Good call. Thank you. Don't let me get away with those mistakes. Other questions? So if one's to an even power or one's to an odd power, you're always going to let u equal the one that's raised to the even power. For sine and cosine. Really, I wouldn't remember, I wouldn't try and make a list of rules in my head though. I would just remember I'm trying to take u equal to the 1 so that after I deal with du, the not u choice has an even number left over. That's the way I really think about it. So let's look at a couple of other examples here. Let's say they are both odd. Let's say we have the integral of cosine to the fifth x sine cubed x dx. Here, any choice will do, but there is a better choice. So there's almost always a better choice, even if you can make any choice. Let me show you what I mean. Here's the worst choice, which we're not going to do, but I'm just going to show you why it's worse. The worst choice would be to let u equal sine of x here. I should point out, by the way, you're not letting u equal sine to the third, you're letting u equal just sine or just cosine or later on just secant or just tangent. But all these problems are u substitutions. So our du here is cosine x dx. And here's why this is the worst choice. If I did it this way, I'm going to pull out one of those cosines. So I'm going to rewrite this as the integral of cosine to the fourth x times sine cubed x times cosine x dx. There's my du. There's sine cubed is u cubed. And okay, trig identity. Cosine squared x is equal to 1 minus sine squared x, which is equal to 1 minus u squared. Cosine to the fourth x is cosine squared squared, which is 1 minus u squared squared. Which isn't impossible by any means, and sometimes you will have to do that. It's just that the better choice here, so we could have done it this way. You have to multiply out 1 minus u squared squared, and then times u cubed. It's kind of gross. If we make the other choice, there's less algebra to do. So it feels extra dark in here. I mean, I know I didn't turn on any lights, but like, which is good, it's easier to see, but it just feels super dark because it's dark outside. The better choice here would have been to let u equal cosine. If we do that, then our du is negative sine of x times dx. I would change the signs and make it a negative du equal to positive sine of x dx. And then instead, we can break up our integral as cosine to the fifth x times sine squared x times sine x dx. And then there's our negative du. There's u to the fifth. And then we don't have to square our trig identity. Our sine squared x, well, we know that sine squared x equals 1 minus cosine squared x. So that's going to be 1 minus this u squared. So that's just going to be a 1 minus u squared. And that's better algebra. Or I shouldn't say better, just less terrible algebra. So simplifying this, we get negative integral u to the fifth times 1 minus u squared du. We multiply it out. We get u to the fifth minus u to the seventh. I would probably distribute the minus sign actually and rewrite this as the integral of u to the seventh minus u to the fifth. And then get u to the eighth over 8 minus u to the sixth over 6 plus c. And then plug in, what is it? I chose u equal to cosine. So I'm going to get cosine to the eighth x, 8 minus cosine to the sixth x over 6 plus c. Gross, but not that gross. It gets grosser. So both odd, you want to pick the one that's to the higher power so you have less algebra to do. One odd, one even, you want to pick the one that gives you an even left over. And if they're both even, because it's terrible. Yeah, we'll come back around to that. It's a special case. So both even is kind of nobody likes both even. Yes. Oh, so I changed. So I didn't want to have it. So I said I have a negative u to the fifth plus u to the seventh, which I just changed. Right, exactly. Yeah. If I see subtraction, a negative of subtraction, I really like distributing and changing the order just because it's not required at all though. So both even is kind of everyone's least favorite. There's a similar situation when you have secant and tangent, which we'll get to in a minute here. But they're both even, it means you don't do a u sub. So no u sub. Just trig identities. Let's see. Yeah, we'll do we'll do two of these. So for example, if I was going to integrate cosine squared x, where both sine and cosine are two even powers. Cosine is squared, sine is to the 0th, even power. You're going to use a trig identity, which is that cosine squared x is equal to 1 plus cosine of 2x all over 2. I personally like to factor out the 1/2. To get the integral of 1 plus cosine of 2x times 1/2. And then we just integrate and we get 1/2 times x plus sine of 2x over 2. Let's see. And then you can distribute the 1/2 and get x over 2 plus sine of 2x over 4. Let's see. So even powers aren't too terrible, they just get messy. For example, if you had, say, the integral of sine to the 4th of x. So that's going to be the integral of sine squared x times sine squared x. And then you're literally just going to replace each sine squared with its trig. Oh, which I suppose I didn't write down. Let me write them down just in case you don't remember them or haven't seen them. Cosine squared x is equal to 1 plus cosine of 2x all over 2. And sine squared x is equal to 1 minus cosine of 2x all over 2. If you add them together, you get 1. Right? If you add those together, the cosines cancel out and you get 1/2 plus 1/2, which is 1, which you should, because it's sine squared plus cosine squared. Okay, so for this one, you have to replace each sine squared with 1 minus cosine 2x over 2. To get 1 minus cosine of 2x over 2 times 1 minus cosine of 2x over 2. I would bring out the 1/2. So I've got a 1/4 out in front. And then I'm going to essentially FOIL out the 1 minus cosine 2x times the 1 minus cosine 2x and get 1 minus 2 cosine of 2x plus cosine squared of 2x. And now for cosine squared, we have to use the same trig identity again. So we're going to get 1/4 times the integral of 1 minus 2 cosine of 2x plus, so let's see, cosine squared of x is 1 plus cosine of 2x over 2. Cosine squared of some other angle is 1 plus cosine of 2 times that angle, 4x in this case, all over 2. Questions about any of the terrible trig identity algebra I've done? Yeah. So one more time.
So the cosine squared of 2x, shouldn't that be 1/2 of cosine squared of 2x? Like, shouldn't there be an extra 1/2?
I pulled out both of these 1/2s.
Yeah, but I'm talking about the last step.
So from here to here. So the identity is cosine squared of any angle is 1 plus cosine of 2 times that angle, still over 2. These 2's are not the same. I mean, I know they're the same, but like one of them's inside a function, one of them's the denominator. The denominator is always 2. No, it's not it's a trig identity. It's not really what you said. We're going to end up dividing by something different when we integrate. So if I were doing this, I would probably do one more simplification. I'd probably factor out a 1/2. Because I don't love fractions. I mean, I do, but like not in that way. So factoring out a 1/2, I get 1/8. And then I've essentially multiplied the insides by 2. Right? If you're dividing out a 1/2, you're multiplying by 2. So that's going to be a 2 minus 2 cosine of, minus 4 cosine of 2x plus 1 plus cosine of 4x. I think now we're ready to integrate. I'll just mentally add 2 and 1 together in my head, just like we're all capable of doing. 2 plus 1 is 3. The integral of 3 is 3x. And then the antiderivative of negative 4 cosine of 2x is going to be negative 4 sine of 2x divided by 2. And the integral of cosine of 4x is going to be sine of 4x divided by 4.
Why is it 3x?
Because I added the 2 and the 1, because I was trying to put things together.
Okay.
Yeah. And then 4 over 2 should be. So powers of sine and cosine, there's 3 different cases. One odd, one even. There's always a one choice to make. Both odd, you make the higher power choice, because it's going to be easier algebraically. And both even, usually on an exam, you won't see anything. The worst you can get is like either sine to the 4th or cosine to the 4th or sine squared times cosine squared. I don't think I've ever seen anyone ask something like sine to the 4th times cosine squared. Because then you have to multiply out 3 of these things. And you get like a cubic kind of like you get more terms than you have a 1 to the 3rd power. So it's just worse and worse. So It can get worse, but usually you don't see much worse than that. At least not in the exam. I could see asking the integral of like cosine to the sixth on a homework question. It's a lot of algebra, but it's not that terrible in the grand scheme of things. Other questions about this one before we talk about secant and tangent? Yeah.
How did that cosine square of 2x?
So wait. So, all right. So for this, for you saying for cosine squared of 2x, what are you saying you want to do instead? And then like so, but I'm letting u equal 2x, and then I'm gonna do a trig identity for that.
Yeah.
Okay. So if I was integrating cosine squared of cosine squared of 2x dx, one way to go is what we did and say, well, that's going to be just the integral of 1 plus cosine of 4x all over 2. The other way to go could be to say, well, we're going to let u equal 2x. So du is 2 dx. You can't see that, can you? And then 1/2 du is equal to dx. So I'm going to replace this with cosine squared of u times a 1/2 du. So then cosine squared of u becomes 1 plus cosine of 2u all over 2 times 1/2. Right? Du. Okay. So then if we integrate this, we've got a 1/4 integral of 1 plus cosine of 2u, which ends up being 1/4 integral. That's going to be u plus cosine, plus sine of 2u over 2 plus c. And if we replace u with what it's equal to, that's where you're going to get the 1/2, the half canceling back out, because you're going to get 1/4 times 2x plus, or maybe not, sine of 4x 2. Let's see. So that's what it would look like doing it that way. It might differ by a constant, which is okay. I guess I'd have to do, okay, fine. Doing it the other way. Integral of 1/2 is x over 2. Integral of cosine 4x is sine 4x over 4. This seems the same. But not just equivalent, the same. They're exactly the same. This, I've got an x over 2 here, and I've got an x over 2 here. I've got a sine of 4x over 8 here. I got a sine of 4x over 8 here. Same thing. Cool. Let's see. Is there anything else I want to say about sines and cosines? Nope. So let's talk about tangents and secants, which have a similar kind of process, but yeah, so I think in the handout, by the way, in the handout, like they kind of break down the rules. They're like, if you have even a nod, you do this. If you have odd, you do this. But let me just kind of, again, give you the broader picture. Let's say I want to integrate, and I want to pick one that's not, I want to pick that one. Let's do the integral of tangent to the 4th of x times secant squared of x dx. And this is for tangent and secant. And what I would say about tangent and secant is anything I say about tangent and secant, you could also apply to cotangent and cosecant. If I say like, one's to an odd, one's to even, you let u equal the tangent, you could also say if you had cotangent and cosecant, the same kind of thing applies. All right, so here I'm either going to let u equal secant or u equal tangent. Let me talk about the wrong choice for a second. If I let u equal secant, my derivative of secant is secant times tangent. That's going to suck up one of those tangents, one of those not u's. It's going to leave me with an odd number of not u's left over, which would be a problem. Let me show you what I mean. So here's the wrong choice. If we let u equal secant, your du is going to be secant x tangent x dx. If I rewrite this, pulling out one tangent and one secant, I've got a tangent cubed, I've got a secant, and then my rest is going to be secant times tangent times dx. Okay, go ahead.
You sub without needing to use trig identities?
Well, I'm not, well, yes. Yeah, that's what I was about to get to. Yeah. But yeah, so here, this would be my, I was using a red pen. Sorry. This would have been my du, and this would be my u, but then, tangent cube is a problem. So instead, right, and here it's more obvious because if you let u equal tangent, your du is exactly secant squared. So then we would rewrite this integral as the integral of u to the fourth times du, which is u to the fifth over 5 plus c, which is tangent to the fifth x over 5 plus c. It's a little more interesting if you have higher powers, like tangent to the fourth x and secant to the fourth x. So now we're going to make the same choice as we did before, right? I don't want to let u equal secant this time just because of the same reason I didn't want to let u equal secant last time. I don't want to have the other function, tangent in this case, have an odd number left over. So here, if we pick u equal to tangent, again, our du is equal to secant squared x dx again. And then if we break this du part off, I guess I could do it though. I really don't. I guess I will one time just for you all because I like you so much. And that sounded kind of sarcastic. I really do like you all a lot. Like I enjoy having you as students. I'm a couple of like I really like it was not just like I don't like doing it this way, but I do like you all. So if I solve for dx here, dx is du over secant squared. I just don't like doing this. It bothers me. And I can cancel 2 of them here, 2 of them here. So I can rewrite this as tangent to the fourth of x times secant squared of x times du. And then tangent to the fourth is u to the fourth. And my not u thing has an even power left over, which is what I'm always going for with these powers of sines and cosines or secants and tangents. Because then we can use my favorite trig identity, I tan, and get sexy. So that secant squared x is equal to 1 plus tangent squared x, or in other words, secant squared x is equal to 1 plus our u squared. So that's what's going to go right there. And then we do this, we get the integral of u to the fourth times 1 plus u squared u, which is the integral of u to the fourth plus u to the sixth, which is going to be u to the fifth over 5 plus u to the seventh over 7. Let's see, which is then tangent to the fifth, 5, plus tangent to the seventh over 7. Let's see. Fun times, yeah.
I have a question. It's not about this question,
Sure.
though, but it has to do with
Yeah.
it. I was looking on this practice problem, and it was like tan x cubed over secant of x, and how would you deal with it if there's like division?
Good question. And the real answer is I don't know the answer yet. So let's talk about something that's not quite this for a second. So the integral was tangent cubed?
Yeah.
Over secant?
Yeah.
Okay, so that's terrible looking. All right, so when I don't know what to do with an integral like this, I would first kind of go to that place and think, well, doesn't seem like it's gonna work because if I let u equal secant, my du is secant tangent. If I let u equal tangent, my du is secant square, which I definitely don't have. Could do that. There's a couple ways to go here. So one way I might think of is just rewriting everything in terms of sine and cosine. That's what probably my first go to. So this is going to be tangent cubed is sine cubed over cosine cubed. And dividing by secant is the same as multiplying by cosine. Right, secant is 1 over cosine, so that's going to be times a cosine x. So what I've really got now is sine cubed x over cosine squared x dx. Okay, so then I think we can try letting u equal cosine. Because if u is cosine, your du is going to be negative sine. That's going to take care of one of these signs, and then there'll be an even number left over. So we can write that as, I'm going to rewrite this as the integral of sine squared x over cosine squared x times dx, sorry, sine x dx. So here's my negative du. Cosine squared is going to be my u squared. And sine squared, well, trig identity time. Sine squared x is 1 minus cosine squared x, which is 1 minus u squared. So the top part's going to be 1 minus u squared. This is going to become the integral of 1 minus u squared over u squared times a negative du. And then we can totally do that by division. This is going to equal negative the integral of 1 over u squared minus u squared over u squared. I'm again going to do the thing where I distribute the minus sign. I'm going to rewrite this as positive 1 minus 1 over u squared. And then we integrate. We get u minus u to the negative 1 over negative 1 plus c. And plugging back in u, we end up getting cosine of x minus cosine x, or minus and minus is plus. Cosine x to the negative 1 is just secant of x. Let's see. Tricky. So a lot of times with these, you have to be kind of tricky sometimes. Sometimes you have to do some manipulation if it's not just this. Another one that's tricky like this is the integral of, say, like cosine cubed. It's a u sub. You know what u is? Sine. Technically, you have cosine to an even power and sine to an odd power. Blah, blah, blah. Backwards, those words. Technically, you have cosine to an odd power and sine to an even power. Right? Sine to the zeroth. Zero is an even number. And it works. Now, maybe it's easier to see if you do the trig identity first. Right? If you actually rewrite this as the integral of cosine squared x times cosine x dx, and then rewrite that as cosine squared is 1 minus sine squared x times cosine x dx. Then it's easier to see, oh yeah, u equals sine makes sense. And my du is cosine x dx. And then you can totally rewrite this as the integral of 1 minus u squared times du, which seems not unreasonable. It just seems really tricky when it's written like that. You're like, well, I don't know what to do. So a lot of times if you have trig things, sometimes rewriting part of it using one of your Pythagorean trig identities is necessary. This would be u minus u cubed over 3, which is sine x minus sine cubed x over 3. We hadn't quite finished the whole story with powers of secant tangent. So let's go back to that for a second. Question? Sure. That's something we can cover. I don't typically, but we can talk about it briefly. I do think I have 1 or 2 examples. So if we had instead the integral of, say, secant cubed x tangent cubed x, and I'm trying to make the choice that gives me an even number of my not u left over. So I picked u equal to tangent, the derivative of secant squared. That's going to leave me with only 1 secant left over, and that's bad news. So I'm going to try going the other. I'm going to let u equal to secant. So if I do that, my du is secant x tangent x, which is going to take care of one of those tangents, and is going to leave me with an even power of tangent left over, which is what I'm looking for. So this is going to become, again, I'm going to write it the way I like to write it. I'm going to pull out the piece of my du that I want. So I'm going to pull out 1 secant and 1 tangent. So I'm left with a secant squared times a tangent squared times a secant times a tangent. And that secant tangent dx is equal to my du. And then my secant squared is u squared. And once again, I tangent gets sexy. 1 plus tangent squared x equals secant squared x. So tangent squared x equals secant squared x minus 1, which is u squared minus 1. Something you'll come to see if you do enough of these problems is that if you have more than 1 term in your answer, all of your answers differ by, the powers differ by 2. So either all your powers are odd or all your powers are even in your answers for these kinds of problems. Here, we end up with the integral of u squared times u squared minus 1, which is u to the 4th minus u squared du. Integrate. plug back in, u equal to secant, so you get secant cubed x over 5 minus, sorry, secant to the 5th x over 5 minus secant cubed x over 3. Okay, so if both powers are even, you have to let u equal, I guess, tangent. If both powers are odd, you have to let u equal secant. I would never remember that in a million years. I remember that I'm just going to try one or the other, and whichever one gives me the leftovers I need is the one I'm going to pick. And then there's two other cases, one of them excellent, one of them terrible. So let's do the excellent one first. Yeah, we got time. We got time. So let's say I wanted to do the integral of, what do I want to do? Not secant. So secant to the 4th, tangent to the 5th. In this case, either choice will do. Because if you let u equal secant, your du will be secant tangent and you'll have an even number of tangents left over. Or if you let u equal tangent, your du will be secant squared and you'll have an even number of secants left over. If I had to pick one of them, I would make the choice of letting u equal tangent. Because I'd rather have a secant squared left over than a tangent to the 4th left over. Because the tangent to the 4th will have to be a tangent squared, which means we're squaring out the trig identity. So here, you could choose either choice is fine, or either, I should say, either choice works, but the one that gives you less leftovers is the better choice. So we would let u equal tangent here, and du would be secant squared x dx. So then this is going to equal the integral of secant squared times tangent to the 5th times secant squared dx. And then you don't have to do it this way. I just found this way to always be like the nicest way to do it. You just write it out again, you pull off the part you need. There's my du, u to the 5th, and 1 plus tangent squared x equals secant squared x. So 1 plus u squared equals secant squared. So that's going to be my 1 plus u squared. And I don't think we need to finish this one because we've done like 6 of these and it's always the same kind of deal. You multiply it out, you have to differentiate. But let's look at, there was one other one I feel like I had on my mind. Oh, I know what I want to say. I will also just point out the same kind of rules are true for cosecant and cotangent. So if someone said like, I'm going to have the integral of like cosecant cubed x cotangent to the 5th x, you're very welcome. I would well, again, I want to make the choice so that I have an even number of leftovers. So if I let u equal cosecant, the derivative of cosecant is negative cosecant cotangent, which will leave me with 4 cotangents left over, which is the right choice. So here you'd let u equal cosecant of x. Your du would be negative cosecant x cotangent x dx. I would change that sign. And I'm going to rewrite this as pulling out a cosecant and a cotangent. So I'm left with cosecant squared x, cotangent to the 4th x, and then here's my cosecant x cotangent x dx, which is my negative du. And cosecant is my u, so that's my u squared. Oh, and I give myself a big enough power that I have to do this trig identity thing. So I know that, do you know the trig identity for cotangent? It's not at 1 plus tangent squared x equals secant squared x, but it's the same idea. Instead of 1 plus tangent squared equals secant squared, it's 1 plus cotangent squared x equals cosecant squared x. So here, cotangent squared x would equal cosecant squared x minus 1, which is u squared minus 1. And then cotangent to the 4th would be u squared minus 1 squared, which is u to the 4th minus 2u squared plus 1. That's what's going to go right here. U to the 4th minus 2u squared plus 1. And then we would do the same sort of thing. We would have negative integral u to the 6th minus 2u to the 4th plus u squared u. We get negative u to the 7th over 7 plus 2u to the 5th over 5 minus u cubed over 3 because I did this distribution. And then we plug back in and we get something. We get negative, cosecant? Yeah, cosecant to the 7th of x over 7 plus 2 cosecant to the 5th of x over 5 minus cosecant cubed x over 3 plus c. Kind of gross. Usually you won't see one to the cosecant and cotangent. It just doesn't come up all that often, although it can. Yeah, there's another one I wanted to. Sorry, I was like, oh, there's another problem. Oh yeah, we need to do that. We got time. Yeah, we got time. Okay, cool. Cool. So I've neglected to talk about maybe some of the most important trig identities or trig integrals that we need to know, like just the straight up basic regular trig function. So we know two of them for sure. You all know that the integral of sine of x is negative cosine of x, and that the integral of cosine of x is positive sine of x. And if you've probably at some point seen what the integral of tangent is. If you haven't, the way you do this is write it as sine x over cosine x. You let u equal cosine x. Your du is negative sine x dx. So your negative du is positive sine x dx. And so it's going to be the integral of negative du over u, which is negative natural log of the absolute value of u, which is negative natural log of the absolute value of cosine of x. Or positive natural log of the absolute value of secant of x. Because you can bring that negative one out in front up as the power of cosine, and cosine of x raised to the negative first power is just the reciprocal of cosine, which is secant. And it's pretty standard to write this in either way. You'll see some people do it like this, and we'll do it like this. It really depends. In the same sort of way, the integral of cotangent of x is the integral of cosine x over sine of x. And if you let u equal sine, your du is cosine, you get the integral of 1 over u, which is the natural log of u, which is the natural log of the absolute value of sine. Which makes sense, because you take the derivative of that, you get 1 over your stuff times the derivative of your stuff. You get 1 over sine times 0 sine, which is cosine. And there, even though you could, nobody writes this as negative natural log of cosecant of x. You totally could. I've never seen anyone do it my whole entire life. But then we've come to the last two. The integral of secant. And I will tell you, there's a story about the integral of secant, which I'm not going to tell you the story because it's probably boring, whatever. But the way that I'm going to show you how to integrate this, or the way we learn it in class, is not how you originally find it. Integrating secant of x actually involves using trig identities and partial fractions, which is kind of neat. And the reason people care about the integral of secant of x, once upon a time, maybe even now, is it actually comes. So I assume all of you have looked at the map at one point in your life, right? Like a map of the world. Yes, okay. And you probably noticed that like Canada looks super huge, right? Even though it's not that huge. Or Greenland looks really, really big on a map because the higher latitudes are way stretched out, right? Even though it's technically the same amount of distance between each latitude, when we try to do this Mercator projection, what's called map, the ones further away from that equator look longer. And what's interesting is the amount they are longer by is the integral of secant of theta, where theta is like the angle. I mean, it's a little more complicated than just that, but integral of secant of theta comes up in talking about the difference in how far the things on the Mercator projection are, which I just thought was super cool. Anyway, if you want to see it someday, after we talk about partial fractions, I will show you how to actually integrate this thing the cool way. Not the cool way, the hard way, the fun way. But to do this, we say, well, someone showed us how to do this once upon a time, so now we know how to do it. So what we're going to do is we're going to multiply both the top and bottom of this fraction by secant of x plus tangent of x. And I'm going to write this out in a very specific way to make it really, really obvious what's happening here. I'm going to write the bottom as secant x plus tangent x, and the top as secant times tangent plus secant times secant, or secant squared. And what do you notice about the top in relation to the bottom? What's the derivative of secant? Secant times tangent. What's the derivative of tangent? Secant squared. So if you let u equal the denominator, du is exactly the numerator. This is u, and that is du. So this is really the integral of du over u, which is just the natural log of the absolute value of u, plus c, which is the natural log of the absolute value of secant of x plus tangent of x, plus c. Pretty cool. These are definitely all integrals you are probably expected to memorize. The last one, I don't remember how to see it. The same story is true for the integral of cosecant. I never remember which way it's supposed to go because technically, so just like cotangent, there are two universally accepted ways of writing the integral of cosecant. So let's move over here since we got room. So the integral of cosecant of x, I'm pretty sure we want to multiply by cosecant minus cotangent. So we get cosecant x times cosecant x minus cotangent x over the same thing, cosecant x minus cotangent x. Pretty sure it's going to work. We'll find out. So on top, I'm going to have cosecant squared minus cosecant cotangent. On the bottom, I'm going to have cosecant x minus cotangent x. So let's see what happens if we let u equal the denominator. So if u is cosecant x minus cotangent x, then my du is, well, let's see, the derivative of cosecant is negative cosecant x times cotangent x, minus the derivative of cotangent is negative cosecant squared, so plus cosecant squared x. And yes, I chose correctly because that's exactly the top. So this is exactly the integral of du over u, which is exactly the natural log of the absolute value of u plus c, which is exactly going to be the natural log of the absolute value of cosecant of x minus cotangent of x. Let's see. Or equally acceptable, negative natural log of the absolute value of cosecant of x plus cotangent of x. Let's see. Either one of them is totally valid, and your teacher should accept either one. But they might have a preference as to which one you actually use. I don't know. Do we have enough time? Yeah, we have enough time. Okay, so these 6 trig integrals you definitely do need to know. They're going to come up again and again and again. Maybe not integral of cos. No, they all come up. So you already know these 2, and the other 4 you should memorize. I have done this in the past. I've told many students, if you have trouble memorizing these, I would encourage you to write them all down on a little card, take a picture with your phone, make it like your lock screen. So that every time you look at your phone, you're like, oh, there's all my integrals of sine, cosine, tangent, secant, cotangent, cosecant. It works. I did it for when I was teaching in class. I was like, oh, I can't remember. There's like these 10 different things that all meant the same thing. It's like, I can't remember these things. I need to learn these things. I'm teaching this. And so I didn't definitely have to learn it. All right, let's do this one. So this is a question that I always asked when I taught 21B, or the equivalent at another college. The integral of secant cubed. And this is the situation where you have a power of secant and tangent. That's the terrible situation. When you have secant to an odd power and tangent to an even power, it's kind of like when you have sine and cosine both to even powers, except worse. So this is a 2-step process, 1 step involving a trig identity and 1 step involving iteration by parts. And you can actually do them in either order you want. So we could either do iteration by parts first and then use a trig identity, or use trig identity first and then iteration by parts. I'm going to do iteration by parts first. So iteration by parts, I'm going to think of this really as secant times secant squared. So if I'm going to think of this as secant x times secant squared x, usually I would focus on what I was going to pick for u first. But since this doesn't really meet the usual criteria, right? I don't have like a mixture of 2 different types of things. It's all trig. I'm going to focus on what should I pick for dv first. So what's easier to integrate? Secant or secant squared? Right. I mean, nobody can do both. We just learned the integral of secant was the natural log of the absolute value of secant plus tangent. But the integral of secant squared is way easier. It's just tangent. So we're going to let dv be secant squared because we know that v is tangent. And then we're going to let u be the other part, which is secant. And then my du is secant tangent. All right, so hold on to your hats. Did I said that twice today? That's terrible. Sorry. I'm not usually a big fan of saying hold on to your hats, but I don't know. I guess there's a lot to hold on for. So the integral of secant cubed is going to equal my u times my v, so secant x times tangent x, minus the integral of my v times my du, which is tangent x times secant x times another tangent x. So I should really just have said tangent squared x. And now this is the part where I feel like people always get stuck. This is the part where we now have to use a trig identity. What's the only thing in my whole expression here that looks like kind of one of your usual Pythagorean trig identities? Right. And tangent squared is equal to what? I tan against x, so tangent squared is equal to. Right. So we're going to replace tangent squared with secant squared minus 1. So we're going to rewrite this as secant x times tangent x minus the integral of secant squared x minus 1 times secant x. And then we're going to distribute. So I've got, let's see, minus the integral of secant cubed x minus secant x dx. I'm going to break this up into two integrals. So write this as secant x tangent x minus the integral of secant cubed x dx minus a minus is plus the integral of secant x dx. Hey, wait, the integral I wanted showed up again. I was trying to find the integral of secant cubed x. So what I'm going to do is I'm going to do two things at once. I'm going to add this integral to both sides. This is kind of like what this is like the other example of a kind of integral where you have to do this thing where you add, like the other example was like e to the x times sine of x or e to the x times cosine x. This is the other one where we do this thing where you get the same integral popping back up. So what I'm going to have here on the left is 2 times the integral of secant cubed x dx equal to secant x times tangent x minus, we just learned that the integral of secant of x is the natural log of the absolute value of secant of x plus tangent of x. And so then dividing both sides by 2, we get that the integral of secant cubed x dx is equal to secant x tangent x minus the natural log of the, I feel like it should be a plus. Oh, it is a plus. Somehow my plus sign here turned to a minus, so it should actually be a plus sign. Sorry about that. The integral of secant cubed x is equal to secant x tangent x plus the natural log of secant x plus tangent x in absolute value, all over 2 plus c. This is a pretty typical example to see in your class at some point. It just is kind of standard fare. I don't know why, but it is. All right, that pretty much summarizes trig integrals in general. I should say trig integrals, not trig substitution, which is a whole other animal. But we definitely needed to do these before we could talk about trig substitution, because you still have to be able to integrate things with powers of trig function after doing trig substitution. I should also say, right, this definitely isn't the end of the story. There's lots of other things that come up, like